I'm Dr. Sreedevi, Assistant Professor, IARE, Hyderabad. Today we are going to the next session of this review of basics in graph theory. Today we are going to see what is Eulerian graph and Hamiltonian graphs. And we will be seeing some theorems associated with that. And we will see what are the conditions for a graph to be Eulerian and how a graph will be Hamiltonian. And we will be seeing the related theorems. Now we will see what is a walk. A walk in a graph is an alternating sequence of vertices and edges beginning and ending with vertices. A walk in which all the edges are distinct is termed as a trail. If all the vertices of a walk are different, then it is termed to be a path. A closed path containing at least one edge is termed to be a cycle. Okay, to see a condition of Eulerian graphs and Hamiltonian graphs, we require all these basic terminologies. Walk, trail, path, and a cycle. Now we will see what is an Eulerian graph. A connected graph is Eulerian if there exists a closed trail containing every edge of G. From the definition of trail, it is a walk in which no edges repeat twice. Here we are giving a graph to be Eulerian if there exists a closed trail. That is such a trail. If such a trail exists, we call it as an Eulerian trail. That is, each edge has to be, that is, if we are given a graph, we have to travel through every edges of graph exactly once. That is, if we are given this graph V1, V2, V3, V4, and we can travel from V1, V2, V3, V4. This is a closed trail, traveling through all the edges of the given graph G. If it is like that, is it possible that you can travel through all the edges exactly once? And closed trail means we have to reach back the starting point. Is it possible to do it like that here? No. Because if we are traveling through this way, from here we can go either this here like that. And again we will be going to the original way we have used, or any of the edges that we have already used. So it is not possible. Now what will be the condition that we have to, what will be the condition for a graph should have to have a closed Eulerian trail, that we will see in the next slides. For now we will see what is a semi-Eulerian. A non-Eulerian graph G is said to be semi-Eulerian if there exists a trail containing every edge of G. That is, it's not a closed trail, but it travels to every edges of G. We will see with examples. Consider this graph, first graph. Here if we are starting through, here I have numbered the edges just to show a trail, how a trail will be going on like this. From 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's a closed trail. That is, I am going through every edges like this. I am covering all the edges of this graph without without going through the edges twice. So it's a term to be an Eulerian graph. Okay. If I'm starting from here, suppose that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Can I reach back the originating point? From here I have started. Can I reach back the originating point? No. But I have traveled through all the edges exactly once. That is, this is not an Eulerian graph, but we can say that semi-Eulerian, because if we are traveling, a non-Eulerian graph is said to be semi-Eulerian if we can travel through every edges of the graph. Okay, this is semi-Eulerian. And what about this graph? If I am starting from this vertex, I go through these edges. Can I go, if I am going through this I will have to walk through any of the edges that I have already walked. Here I am going this. Here if I can't take this path, and again I have to go through this way. If I am going like that, I am unable to travel through every edges exactly once. So it is not an Eulerian graph. This is an Eulerian graph, this is semi-Eulerian, and this is non-Eulerian. In common language, what is an Eulerian graph? Can be said as a diagram that can be drawn without lifting one's pencil from paper and without repeating the lines. I think you remember me saying who is the father of graph theory? Yeah, Euler. And why? Till then, by the solution of on real life problem of Königsberg. This is river Perigal, and the city of Prussia is situated on either side of river Perigal, like this A, B, and this city has two more islands, landmasses C and D, which are being connected with 7 bridges. 1, 2, 3, 4, 5, 6, 7. And someone proposed the problem whether it is possible to start from any of these landmasses, go through these 7 bridges exactly once, and have to reach the starting point. It was the famous mathematician Euler showed that it is not possible. It was the first time that a graph has been used to picturize a real life problem, and this has represented the graph, the real life situation as this 4 landmasses as 4 vertices, and these 7 bridges were connected with 7 lines like this. C is connected with A with 2 times, so he put some parallel edges. Here also, C and B. This is the situation where it is been kind of short, and it has been short that we cannot go through these 7 edges of this graph exactly once and reach back the starting point. And because this term, the Eulerian trail was lost because of Euler. Was the first problem to solve the Königsberg bridge problem. Okay, that is, we have to travel every edges of the graph exactly once without repeating the path that we have taken. Now we will go to see what are the conditions. If a graph is Eulerian, then we have, in that condition, we have shown that for an Eulerian graph, if such a path is, such a tour is possible, then the very vertex of graph should be of even degree. Now we are saying what are the conditions of a graph to be Eulerian. A graph in which degree of each vertex is at least 2, then G contains a cycle. If G is a graph in which degree of every vertex is at least 2, then G contains a cycle. How we can say that? Suppose that every vertex of G is of degree 2. Then we can find a walk from vertex, let it be V0. We can start a vertex V0 and we can go to V1. From there V1 to V2. Because every vertex is connected with at least, every vertex is of at least 2 degree. And from V0 to V1, from V1 to V2, and so. Since this graph, we will reach a vertex Vk, and from there we have to reach back to V0. Why? Because we have been given that every vertex is at least 2. So we will be passing through all the vertices. Then we will find a cycle. If a connected graph is next condition is a connected graph is Eulerian if and only if the degree of each vertex is E. We have seen that in our examples, this connected graph. We have seen that it is to be Eulerian. And see the degree of each vertex here. Here it is 2. What about here? 1, 2, 3, 4. Here also 4, 4, 4, 4, 2. A connected graph is said to be Eulerian if the degree of every vertex is of 2. Then a connected graph is Eulerian if and only if the set of edges can be split up into disjoint cycles. We have seen that a graph in which degree 2 contains a cycle, and if it is a cycle graph, it can be it is Eulerian if and only if its edge set can be split into disjoint cycles. Suppose we are finding one cycle. If the cycle contains all the vertices of G, then that's okay. If we are not finding, if we are finding some other vertices, then we can disconnect those edges cycles, and we can find another cycles. And the union of all these cycles will constitute a Eulerian graph. A connected graph is semi-Eulerian if and only if it has exactly 2 vertices of odd degree. Here, how many vertices are of odd degree? Here we are one vertex of degree 3 and another vertex of degree 3. And here it is 4, 4 and 2. So any connected graph is semi-Eulerian if and only if it contains exactly 2 vertices of odd degree. Okay? These are the conditions when a graph is said to be Eulerian. A connected graph is Eulerian if and only if the degree of every vertex is even. Connected graph is Eulerian if and only if the set of edges can be split up into disjoint cycles. A connected graph is semi-Eulerian if and only if it has exactly 2 vertices of odd degree. Now we will see this Fleury's algorithm. Fleury's algorithm gives an Eulerian trail in a given graph. Let G be an Eulerian graph. Then the following construction is always possible and produces an Eulerian trail of G. Choose an arbitrary vertex V0. Okay, then let it set the walk W0 to be V0. Suppose we can have a trail. Trail means an alternating sequence of vertices and edges in which no edge repeat. Suppose we have a trail Wi such that V0, V1, E1, etc., EI, VI. Suppose we choose this trail. Then choose an edge EI plus 1 which is not in this one, not considered earlier, in such a way that EI is incident with this vertex VI. If there is no other alternative, only unless there is no alternative, EI plus 1 is not a cut edge of this GI, where GI is G difference E1, E2, etc. EI. That is, we have to consider this EI plus 1, which is not a cut edge. If there is any opportunity to connect an edge which is not a cut edge, we have to choose that EI plus 1 like that. Stop the step 2 when no longer can be implemented. If G is an Eulerian graph, here we have seen that we can see that every vertex is of even degree, right? 1, 2, 3, 4, 1, 2, 3, 4. Here also it's and like 2. So it's an Eulerian graph. And from this, from any Eulerian graph, we can find a Eulerian trail using this Fleury's algorithm. Here, if you are applying this, here I can start from any of these vertices. Here, can go through these edges and reach back this. By apply Fleury's algorithm here to find this Eulerian trail. How we can apply here? Starting this from here, it is considered to be V0. From here, I can start to this vertex. Let it be 1. From here, I can go to this 2. From going here 3. From again going here. From here, I have to choose I have no other way to choose any other edge. So I have to choose this edge, 4. From here, I am going to this 5. From here, the 6 can be taken. From here, 7. 6 to 7. 7 to this 4. 4 to 6 again. From here, I am using this edge. Again, I am using this edge. This is giving an Eulerian trail starting from U. which is according to the Flickr algorithm. We are adding each edge one by one, such that we haven't used it ever before. Okay, this is the condition of Flickr algorithm in this given Eulerian graph. If you are applying this Flickr algorithm from this vertex U, you are going to 1, then 2, 3, then again U, then from there you are going to 4, 5, 6, 7, 7 to 4, 4 to 6, 6 to 2, 2 to U. Okay, this gives a condition for finding an Eulerian algorithm gives a condition for finding an Eulerian trail in a given Eulerian graph. Now we will see what is an arbitrary traceable graph, Eulerian graph. Consider this Eulerian graph. Is it Eulerian? Yeah. If we are starting from any of these vertices, we can go back to the reaching the starting point. But according to this, we have to choose our edges arbitrarily, right? If we are starting from A and I am going to B, from A to B, from B to C. From C, I have options either to go to E or D or A. If I am going back to this A, can I trace the whole graph? No, it's not possible. Which is not an Eulerian line of this graph. Hence, you won't be getting the entire Euler circular line simply moving the edge that we have not traveled ever before. So, we have this arbitrarily traceable graph. Or what it is, we will see. An Eulerian graph is arbitrarily traceable from a vertex V if whenever we start from V and travel the graph in arbitrary way, never using the edge twice, we eventually obtain an Eulerian trail. Suppose if I am starting from this vertex here, let it be K. I can take these paths from here to here, here, then here. Instead of going here, I can go back here also, right? Then will I get an Eulerian trail of this graph? No. But if I am taking this vertex V, I can have this path, right? I can either go through this, but if I am taking this way also, it is possible. Again, I can go through this ways. This complete Eulerian trail is derived from this graph. So this is from V if you are starting like that. Suppose if I am starting, instead of starting from V, I have started from this vertex. I am going through this way. I am taking no other way which I have traveled ever before. I could bend through this way and this. Could I complete the graph? No, because it was not possible. I should have taken, even though it is like that for constructing an Eulerian graph, it is like that we can travel to the edges in such a way that we have not taken it ever before. It is not possible to complete an Eulerian trail if we are starting from here, like that. Okay, but if I am starting from here, and in whichever way I go, I will be getting a Eulerian trail from this path, this starting point. So this Eulerian graph is arbitrarily or randomly traceable from a vertex V if whenever we start from V and travel the graph in an arbitrary way, never using the edge twice, we eventually obtain an Eulerian trail. Okay. Now consider these graphs G1 and G2. Can we say that they are arbitrarily traceable or not? If I am starting from this vertex, I can go through this and come through this here. It's like that. If I am taking this path, will I get a complete Eulerian graph? No. Right? I had to go through this way early. Then it is completely Eulerian graph itself. But if I am also starting from this vertex, What will happen if I am going through this phase? Did I get that complete Eulerian trail in this graph? No. So this graph is an Eulerian graph, but it is not arbitrarily traceable. But when I am considering this graph G2, I take this vertex. I found it has not been traveled earlier, so I went through this. I found this one. Again, the edges which not traveled ever before. And I'm reaching back. This graph is arbitrarily traceable. G2 is arbitrarily traceable from any vertex, whereas G1 is not arbitrarily traceable from any other vertex. Okay? The Eulerian graph is said to be arbitrarily traceable and non-arbitrarily traceable. The condition, I hope it is okay for you. Now we have an important result. An Eulerian graph G is arbitrarily traceable from a vertex V if in G, if and only if every circuit in G contains V. Suppose this, if it is V, is that V contained in every circuit in G? No. But in this condition here, if I am taking this U, it is contained in any circuit in this graph G, right? If I am starting from this or starting in this G, U is contained here. But this V is not contained in every circuit in this graph. So a condition for what is a condition for our graph to be arbitrarily traceable from a vertex V? That V must be contained in every circuit of the graph G. Okay? Now identify the following graphs as Eulerian, semi-Eulerian and non-Eulerian. If you are taking K5, what is K5? Complete graph on 5 vertices. Is it Eulerian? We'll see. V1, V2, V3, V4, V5. Complete graph means every vertex is adjacent with every other vertices, right? V1 is adjacent to V2, V3, V4, V5. V2 then adjacent to V1, V2. Sorry. It's a complete graph on 5 vertices, K5. Is it Eulerian? For a graph to be Eulerian, what is the condition? We should travel every edge exactly once and reach back the starting point. Okay, is it like that? Can we find such an Eulerian trail in this graph? Suppose I am starting from V2. Then I can go through these edges. Then, second line is how we have drawn. Suppose from here, I can take this two. Yeah, it's an Eulerian, right? Thus K5 is Eulerian. What about K23? What is K23? It's a complete graph, complete bipartite graph with 2 vertices on one side, one partition, and 3 vertices on other partition. That is, we have 2 vertices in one partition and 3 vertices in another partition. If every vertex in one partition is adjacent to every other vertices in the other partition. If such happens, then we call that partition to be complete. Here, we are starting from here. Okay, we got a Euler trail here, but can we complete it to a closed Euler trail? No, because we started from here, V1, and we ended in V2. U1, U2, U3. Okay, it's a non-Eulerian graph, but we got an Euler trail in this graph because we travel through every edges exactly once. So it is semi-Eulerian. And what about this graph of this cube? So this K5 is Eulerian, K23 is semi-Eulerian. And what about this graph of cube? Yeah, we know this how the graph of cube will be. Is it Eulerian? Because from the very first side we can see that every vertex is of degree or degree. Graph to be Eulerian, it should be every vertex should be of even degree. No need to try for all this, go through this all tour and all. Okay, so it is not Eulerian. And what about this Peterson graph? Peterson graph, I think we have discussed earlier in our lecture series. It's a 3 regular graph with 10 vertices and 15 edges. Okay, there are also 3 regular graph. So it is not every vertex. What is the condition that we had? A connected graph is Eulerian if and only if the degree of each vertex in G is even. So Peterson graph, every vertex is of odd degree. It is also non-Eulerian. Okay, so what is Eulerian graph? What is an Euler trail? And some examples of Euler trail and some algorithm, that is Floring's algorithm to find an Eulerian trail of a given graph we have discussed. Now we'll be going to see what is a Hamiltonian graph. A Hamiltonian circuit in a connected graph is defined as a closed walk that travels through every vertex V of every vertex of G exactly once, except the starting vertex at which the walk also terminates. That is, we are getting a closed walk. Closed walk which travels through every vertices means we are taking a closed path. If the closed path, if we just a closed path means it's a cycle. If that path goes through all the vertices of the graph, then it is termed to be a Hamiltonian circuit. Now consider this graph. If we are starting from here, I can go through this. And I have gone through all the vertices, right? This closed path has gone through all the vertices of the given graph. So it is a Hamiltonian circuit. Now suppose starting from any of these vertex like this here, from where we can go. If it is like that here, from here I can go through this here, from here, here, here. Which all ways I can travel. Starting from this vertex, I can go through all these vertices. I could go through all the vertices. From here, it is like, consider this vertex. From here V1, if it is V1, if I can come to V2, from here V3, from then I am going to V4, then V5, from here V5 I am going to V6, from V6 I am going to V7, from here V7 I am going to V8, from V8 I can go to V9, then V10, from V10 to V1. So that is, I could find a path, closed walk that travels every vertex of this graph. So this contains a Hamiltonian cycle or Hamiltonian circuit. Now we will see what is a Hamiltonian circuit is. A circuit that in a connected graph is said to be Hamiltonian if it includes every vertex of G. That is, if we can find a circuit that passes through every vertices of G, then that circuit is termed to be a Hamiltonian circuit. In a Hamiltonian circuit in a graph G with n vertices, there will be exactly n edges. Okay. A non-Hamiltonian graph is said to be semi-Hamiltonian if there exists a path passing through every vertex. but it will not be terminating at the initial vertex. It can be obtained from Hamiltonian circuit by removal of one edge. Okay. Analogously with this Eulerian graph, semi-Eulerian, here we are having semi-Hamiltonian. Here we can see this Hamiltonian graph. If I am starting from any of these vertex, I can go through any of these vertices and reach back the original or starting point, originating point, and it is Hamiltonian. If I am starting from this vertex, I can go through this vertex. Can I reach back it? No. It is semi-Hamiltonian because I can find a tour through every vertex of this. From here I can go through like this. Here I can go through like this. From here I can go from here to here. Is it possible? Is it Hamiltonian? No, because I am using this answer twice. So it is not a Hamiltonian circuit. It can be taken like this. I can go through this. Consider this. Now consider this one. From here, if I am starting any vertex, start from any vertex. From here, I can start, go here to here. Then from here, it's okay. Can I go to this vertex? No. This is non-Hamiltonian. Okay. If I am starting from this vertex, if I am going here, I can't go to other vertices. Similarly, the same thing. So this is Hamiltonian, semi-Hamiltonian and non-Hamiltonian graphs. Now see whether these graphs are Hamiltonian or not. Suppose this we can, in this first figure, I am starting from this vertex. Can I go through other vertices? I can go through this vertex. From here I can go all these vertices. From here I can go to this. From here. I'm traveling through all the vertices exactly once. So it is a Hamiltonian graph. And what about this one? Here I am going through this vertex. From here, starting from this vertex, I can go to here, then here. Then can I go to this vertices? No. Suppose if instead of taking this path, if I am taking this, I can go this much. I can't be able to go to the other vertices. So it is not Hamiltonian. And what about this one? If I am starting from here, I can go through all the vertices. But am I reaching back to that original vertex? No, it is semi-Hamiltonian. Okay? Yeah, we have seen this in case of Eulerian graph if you arose as a real life tableau. Here also this Hamiltonian graphs also arose as a part of a real life puzzle, around the world puzzle. Actually in 1857, Irish mathematician Sir William Rowan Hamilton invented this puzzle. It consists of a regular dodecahedron, a polyhedron with 12 regular pentagonal faces as shown in figure. It's not regular because I had to elongate my figure to fit into the slide and all. It's not regular pentagonal faces, but it's like that only. Each vertex is where this 20 vertices and 12 regular pentagonal as shown this here. Each vertex represented a major city of the world, and each edge between the vertices represented the route between the cities. The problem, what was the problem? Beginning at an arbitrary city, find out a tour along the edges that passes through each city exactly once and return to the city of origin. Was it possible? The problem arose, and it was this Sir Hamilton represented the real life situation to another figure like this. It's a pentagon. These 20 cities have been replaced like this, and their connections were replaced like this. Okay, 1, 2, 3, 4 like that. It has been placed, and whether it is possible to connect all these 20 cities exactly once, going through these 20 cities exactly once. That problem was proposed and it was shown like that. Okay, this was a this real life problem, that is around the world problem, was the kind of this real life condition of around the world puzzle gave birth to this Hamiltonic circuits. Okay, if G is of order n, that is number of vertices of G is n. What is the general nature of that graph that is guaranteed to have a Hamiltonian circuit? Actually, if a complete graph with 3 or more vertices is on such case. What is complete graph on 3 vertex? It is just our triangle. So this complete graph on 3 or more vertices is guaranteed to have a Hamiltonian circuit in it. But unlike, we are given some conditions in Eulerian graphs to say whether the given graph is Eulerian or not. But here, whether a given graph contains a Hamiltonian circuit or not is an unsolved problem in graph theory. So the number of edge disjoint circuits in edge disjoint Hamiltonian circuits in a graph is also unsolved problem. But we have some ideas, results giving some idea of whether given graph is Hamiltonian and all. And what is the condition of edge disjoint Hamiltonian circuits in a graph? In complete graph with n vertices, there are n minus 1 by 2 edge disjoint Hamiltonian circuits if n is odd and n is greater than or equal to 3. That is, if 5 vertices k5, we have 5 minus 1, 4 by 2 edge disjoint Hamiltonian circuits. Okay. And now we will be seeing some theorems on the condition of Hamiltonian circuits, because earlier in Eulerian graphs we were given certain conditions to check whether the given graph is Eulerian or not. But here we don't have any such conditions or restrictions to check whether the given graph is Hamiltonian or not. But some graphs, some results have been shown to give some restrictions, or if it is satisfied, then it will be Hamiltonian, or if it is not satisfied, it will not be Hamiltonian. But it has its own restrictions in that area. Now we have seen that in complete graph with n vertices where n is odd and n is greater than or equal to 3, we can have n minus 1 by 2 edge disjoint Hamiltonian circuits. If a simple graph G, we will see this Diox Theorem, which states like that: a simple connected graph G with n vertices n where n is greater than or equal to 3 is Hamiltonian if degree of V is greater than or equal to n by 2 for every vertex V of G. That is, if you are given a graph with n vertices, and if the degree of every vertex in that graph is greater than or equal to n by 2, then the graph is termed to be Hamiltonian. We'll see whether it is okay. It's not. For example, consider this figure. Here, how many vertices are here? Here, how many vertices? This first one. 1, 2, 3, 4, 5, 6, 7, 8. So n equal to 8. And what is degree of? What is the, according to Diox condition, what is expected? If every vertex is greater than or equal to the degree of n by 2. That is, if degree of every vertex V is greater than or equal to n by 2. Here n is equal to 8, so n by 2 equal to 4. If every vertex is of degree greater than or equal to 4, then it is a Hamiltonian. But here it is every vertex is of degree 3. Right? Even though this graph has turned to be Hamiltonian. Here we can say that it is not Hamiltonian just because here 6, every vertex is not of degree greater than or equal to 3. It is not Hamiltonian. It's not Hamiltonian. Here we can't say like that. That is, Diox theorem is not necessary to tool to state whether a given graph is Hamiltonian. Okay, Diox Theorem is not a necessary tool. It is not sufficient to prove whether the given graph is Hamiltonian. Now just this OR's theorem. It is also a condition to perhaps OR's theorem also gives an insight whether the given graph is Hamiltonian. Now just about, let's see the statement. Let G be a connected graph with n vertices, where n is greater than or equal to 3. If degree of u plus degree of v is greater than or equal to n, for every pair of non-adjacent vertices u and v, then G is Hamiltonian. Okay, that is for every non-adjacent vertices we are taking. If we can find that degree of u and sum of the degrees of u and degrees of v to be greater than the number of vertices, then the graph is considered to be Hamiltonian. Here, what is that? How many vertices are here in this figure? 5. And consider this in any non-adjacent vertices. Suppose I am taking this A and C. And the degree of A plus degree of C is 3 plus 3, 6, which is greater than 5. The graph is Hamiltonian. Okay, no problem. Here, what about this? Here, we can take from this. Here it is 3. Here it is 3. Non-adjacent vertices. I am taking the sum. How many vertices are here? 1, 2, 3, 4, 5, 6, 7, 8. So n equal to 8. And degree of u plus degree of v is 6, which is less than or equal to 8. Right? It is not greater than 8. Greater than or equal to 8. Even though it is the case, this graph is Hamiltonian, because we can find a Hamiltonian circuit connecting each and every vertex of this graph. That is a tool. Hamiltonian circuit means a tool that we can pass through every vertex of the given graph exactly once without going through it twice. Okay, so this is a Hamiltonian graph, even though the OR's condition is not satisfied. So this OR's theorem and Diox theorems are not sufficient to prove whether the given graphs are Hamiltonian. Now we will see this traveling salesman problem. Mostly we have heard about this traveling salesman in our school classes itself. What is that? A person who has to travel through all different cities and have to reach back to the city of origin with less cost of traveling. Okay, for example, consider this problem. Traveling salesman wishes to visit several given cities and return to his starting point, covering the least possible distance. Consider this problem. Consider this figure. Okay. And vertices are named A, B, C, D, and the edges are given like this. Now we can see that it is a weighted graph. Why? Because every edge has been assigned a real number, positive real number. It is termed to be the weight. Actually, this BD, I have forgot to put this weight 3. Okay. And this is a weighted graph. And we want to see this. Out of this, we have to find out of one of the problem applications in the weighted graph is shortest path problem. And here we are asked to find, we have to reach the starting point itself with less cost. One of the possible ways means we can find this different possibilities connecting. Like, if there are five cities here, it is okay. We can find this 5 minus 1, 4 by 2, 4 by 2, 2. This different Hamiltonian cycles. But if the number of cases increase, that is number of cities increase, these possibilities is too difficult to find out. So we are applying the shortest path techniques here. From here, we can apply the shortest path technique that we have discussed in this review of basics 5. Using the shortest path techniques, we can find a path from A to B, which is here A to B. I think it's distance 2. From B to C, B to D, 2 plus 3, 5. And from here D to E, it is like D to E is 5. D to E it is 5. Then it is then E to C it is 9, and E to C it is 8, and C to A which is 8 again. That is the shortest path. We are using that shortest path problem that we have discussed earlier in this path cycles and all. Okay. So the task of finding this edge disjoint Hamiltonian circuits is too difficult when it comes to the graphs with larger number of vertices. Now this Chinese postman problem. It was first posted by Chinese mathematician Mi Q Quan. And the problem is that a postman wishes to deliver letters covering the least possible total distance and returning to the starting point in such a way that he must travel each road on his route at least once. But he should avoid covering too many roads more than once. That is, he has to go through each route and has to reach back to the at least he has to go through each route at least once and should avoid covering going through the roads more than once. Solution. Putting this, we can solve this Chinese postman problem. We have to put it into a weighted graph. Where graph corresponds to a network of roads, where the vertices of the graphs corresponds to a network of roads, and this weight on this each edge defines the distance between the points. And Chinese postman problem. The problem was first posted by Chinese mathematician Mi Q Quan. The problem was a postman wishes to deliver letters covering the least possible total distance and returning to the starting point in such a way that he must travel each road on his route at least once. He should travel at least the roads which is assigned to him, he should travel at least once, but should avoid covering too many roads more than once. Okay, so how we can find a solution to this problem? Here we are asked not to travel the roads much more times. Okay, so we have to find a weighted graph where the graph corresponds to a network of roads, right? And the weight of each edge corresponds to the corresponding distance between the points. The requirement: find a closed walk that with minimum total weight that includes each edge, and such a tool is referred to as an optimal tool. If the graph is Eulerian, that is, we are starting from one edge, we can go through all the vertices or all the edges exactly once and reach back the starting point, then it's okay. The given graph, if the graph is Eulerian, then Euler trail of a closed walk is of the required type. We are safe. If the graph that we obtained is Eulerian, then we have nothing to worry, because we are starting from one point and we are going through all the edges exactly once and reaching back the same point. Now, if it is not Eulerian, then any optimal tool, that is a tool in which traverse some edges more than once with less weight. We have to find that. For example, consider this figure with vertices U, X, U, W, Y, Z, V. And these all are connected with all these paths. And this all connected with this. It is weighted, and it is suppose it is the distance between these vertices. If it is we have to find this optimal tool, right? So we can find that from X to U, we can find X to U, it is distance point. First we are traveling there from U to Y, then Y to W, W to V, W to V, then V to Z, Z to W again, then W to Y, Y to X, then from there X to U, U from U to W again, then W to V, V to X, and X to Z, and Z to Y, and Y to X. That is, we started from X and we are ending with X, but we are using some edges again and again with less weight. Okay, it is optimal tool. It is the optimal tool, though we have used this edges XU and WY. And XY and WV. We have used these 1, 2, 3, 4 edges twice. But even though we have used these 4 edges twice, it is considered to be the optimal tool of this figure. You can see this. Thus, we can rephrase the Chinese postman problem. If given a weighted graph with non-negative edge weights, by duplicating an edge, an Euler weighted supergraph G star of G can be found, such that this, when an edge is an edge of that G star, which is not an element, not in the edge of G, it should be as small as possible, and find an Euler tool of this G star. That is rephrasing Chinese postman problem that we are finding. We first find a graph of the given situation. Then we find the duplicating by duplicating edges of G. We find an Eulerian. We are finding an Eulerian weighted supergraph. Instead of finding, we were using subgraphs. Now we are using supergraph, like a graph which contains the given graph G star of G, such that if E is an edge of this G star, that is edge set of G star, which is not an element of that edge of E, as edge of G, with W of E should be as small as possible, and find an Euler tool of this G star. So this edge duplicating, I think we have not discussed earlier. An edge E is said to be duplicated when its ends are joined by a new edge of weight itself. Suppose that I have this edge U and V connected with this edge of weight, if it is 1. If these ends are again connected with another edge whose weight is again 1, then it is said to be, this edge is said to be duplicated. Okay, an edge is said to be duplicated when its ends are joined by a new edge of weight of E itself. Okay, suppose we had this original situation of the original situation of the postman, where he had this vertices X, Y, Z and U, V, W. Now we are rephrasing the situation to such a condition like this, where these edges with least weight are being duplicated. Here this 1, then 1, then is there any, this 1, 2, then this 2 is duplicated. Okay, here this one. Now we are given, now the condition of given graph turns to be, here the graph was not Eulerian. Now here the graph turned out to be Eulerian, right? You can see just what is condition for Eulerian graph. If every vertex is of equal degree, then it is an Eulerian graph. Here also this 4, 1, 2, 3, 4, 5, 6. Here 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Here 1, 2, 3, 4. And here also this even degree. So every vertex turned out to be even degree and it is an Eulerian graph, and now we can find an Eulerian tool using Flickr algorithm or anything. So it is equal. That is Chinese problem can be, Chinese postman problem can be observed that it is equivalent to Chinese postman problem follows from the observation that a tour of G in which each edge E is traversed m times corresponds to an Euler tool in the graph obtained from G by duplicating E m minus 1 times. That is, here we have traveled these edges twice, and we have obtained this, we have traveled through this edges twice, and this it has been how many times this they have been duplicated? T minus 1, one time it has been duplicated. That is, it follows from the observation that a tour of G in which each edge E is traversed m times corresponds to an Euler tour in the graph obtained from G by duplicating that edge E by me minus 1 times. And if we are duplicating the edge E with me minus 1 times, then we can find an Euler tour through that edge with me times. Okay, that is, if we are duplicating an edge E with me minus 1 times, then we are traveling through that again me times. Because why this me is put is that to specify that edge E. Now we have seen what all in these things, when a graph is said to be Eulerian, and when a graph is said to be Hamiltonian, and what is the conditions for Eulerian graphs, and some an algorithm to find an Eulerian trail of a given Eulerian graph. Then what are the some theorems related to the conditions of finding Hamiltonian graphs. And now we have discussed 2 real-life problems of around the world puzzle, and this around the world puzzles we can use Hamiltonian circuits, and this traveling salesman problem that also corresponds to this Hamiltonian circuit, and Chinese postman problem, it corresponds to the application of Eulerian graphs. I hope you have enjoyed all these things. Thank you for watching. Thank you. Thank you so much.
Like, share and subscribe. Hit the bell icon for more updates.